Okay, let's solve a problem, a very simple steam power problem using an ideal Rankine cycle. So let's see what information are supplied. Steam enters the turbine at 4 MPa 400 degrees Celsius. So therefore state 1 is given to us and is condensed to a pressure of 100 kPa. So the condenser pressure is known. Determine the thermal efficiency of the cycle. Okay, let's go one step at a time. So state 1, four MPa is 4000 kPa and 400 degrees Celsius. So our goal would be to find enthalpy and probably entropy. So how do you calculate or find the enthalpy? First step in a PC model is to determine the composition of the state. Is it a superheated vapor, liquid, or mixture? Our guess would be it would be a superheated steam, but let's figure out the ideal way to do that is to draw the dome and do a constant pressure line on it. It's a very high pressure line, so it's 4000 kPa. So where would be state 1? We know this is 4000 kPa line, so therefore the state must be somewhere on this black line. And wherever the temperature is 400 degrees Celsius. So to figure out the state, you find the saturation temperature TESTapp at 4000 kPa, and that's this temperature. So let's see how we find the saturation temperature. We know the pressure, so we go to the pressure table. Okay, let's open another window. And go to the property tables. And in the PC model, steam, you go to the saturation pressure table and go for pressure is 4 MPa. At 4 MPa, the saturation temperature is 250.4, 250 degrees Celsius. Remember, steam tables are in Celsius, not in Kelvin. So about approximately 250. So this temperature is only 250 degrees Celsius. And our state 1 is 400, so it's way above that. So state 1 will be somewhere here. So that means state 1 is superheated. So how do we find, say, enthalpy at 1? We now go to the superheated table of H2O. This is the superheated table. Find the 4 MPa table. 4 MPa is somewhere 1 MPa here, 2.5, 4 MPa, and 400 degrees Celsius is here. So enthalpy is 3213 and entropy is 6.769. So we go back and jot these numbers down. So enthalpy at 1, 3214, and entropy at 1, 6.769. Standard SI unit, so I'm not writing the units here to save time. So how do we figure out state 2? That's a little more complicated. State 2 is what? The turbine exhaust, and we know that pressure is much lower. Actually, pressure is given to us 100 kPa. And in the turbine, entropy remains constant, so state 1 to 2 is isentropic, so entropy at state 2 is known. Also, Also, we do know that pressure at this state is 100 kPa. So now that we know the pressure and we know the entropy, we have to figure really if 2 is really in between the F and G state or not. We just randomly drew one here. If I drew one up there, then state 2 would be superheated. So right now we have no clue whether state 2 is inside the dome or if state 2 is superheated or not. So to figure that out, let's try to find what is SF and what is SG. And if we can bracket, if we find that S is somewhere in between SF and SG, then we got the state. Okay, because there is not enough space here, I'll go and redo this in the next page. So let's go find state 2 here. Once again. Okay, so let's write down what we know about state 2 again one more time. Pressure is 100 kPa and entropy is known. Okay, so to find SF at 100 kPa, because remember this is the 100 kPa line, so this is my F point and this is my G point. SF at 100 kPa and SG at 100 kPa we can easily determine by going back to the table. We know the pressure, so we'll again go to the pressure saturation table. At 100 kPa we can pick up SF and SG. We'll also pick up HF and HG and write this number down. So SF is 1.3026 and this is SG, and the same token as HF, we may need that a little later, so I'm just being methodical here. Okay, note that our S is in between these two values. So obviously 2 must be in between F and G. And that's how we detect the phase composition of the state. If suppose this was S2, these are of course 2, S2 is suppose bigger than 7.35. In that case, we have a superheated state. But now that we know it's a mixture, we have to figure out what is the quality of the mixture. How do you do that? We know it's given by S is given by 1 minus X times SF plus X times SG. In other words, X is the weight. You can see that if X equals 0.5, if quality is 0.5, then S becomes SF plus SG divided by 2. But so if X is 1, you can see that we get S becomes SG, X equals 0, then we get SF. So S must be in between SF and SG, weighted by X, called the quality. The higher the quality, X is closer to 1. Okay, so we already know what is SF. We figured that out. This is our SF. We know what is SG. And S is also known. Solving, we can find X to be approximately 0.9. Now that we know X, and we already SF and HF and SG we already determined, therefore H also we can find 1 minus X times HF. Again, weighted average of the enthalpy at the F and G state. And if you substitute the known values, here is HF is known, Hg is known, and X is known. We just found it. So therefore, H can be calculated to be 2455. So now that we found state 1 and 2, we can go and analyze the turbine. Recall the turbine formula. Okay, now let's get the condenser exit temperature state. Recall this was our state 2, and after that the steam is cooled to state 3, which is a saturated liquid. So state 3, we know in ideal Rankine cycle there is no pressure drop. So pressure is same as pressure 2, which is 100 kPa. And temperature, and we know the quality because it's saturated. At state 3, it's F state. So that's important thing to remember. X equals 0 for F state and X equals 1 for G state. So how do you find with after enthalpy? So what is enthalpy at state 3? It's quite simple. We go back to the table and at 100 kPa, 0.1, if we go pick up what is enthalpy, it's 417.5. Okay, to find state 4, which is a subcooled liquid, we have liquid at state 3, and with a pump, isentropic pump, we are raising the pressure. So this is the liquid zone, and for the liquid zone, we got to know that we use a sub model called the subcooled liquid model. If you go to the handout, for instance, if you go to understand the model, you go to table J right here. And if you browse all the way down, you will find all the material model explained, the formulas explained here. And let's go to the PC model. In the PC model, as you can see, this is the CL submodel, the compressed liquid or subcooled submodel. V, U, and S are function of T only. That's the important thing about this model, that specific volume, U, and entropy, they do not depend on pressure. As a result, if we want to find, for instance, any state in the subcool, as long as you know the temperature, then V is same as Vf at that temperature, U is same as Uf at that temperature, and S is same as Sf at that temperature. So you know in an isentropic pump, the entropy doesn't change. Therefore, you can see that because entropy depends on temperature only, in a pump temperature also doesn't change. So even though when we plot something in a TS diagram, we exaggerate, we show, oh, state 4 is up there. In reality, state 4 is really on top of state 3 on a TS diagram. If you draw some other diagram, HS or something, then you can see the difference. But in a TS diagram, really 3 and 4 are almost on top of each other because of this. So to find enthalpy at 4, what should we do? To find enthalpy at 4, so we know that enthalpy depends on U plus PV. And we know U is a function of temperature alone, and P times V, which is a function of temperature alone. And we know because entropy remains constant, that implies T4 equals T3. So therefore, enthalpy can be found from UF at T3, which we know, plus P VF at T3. We can go pick up these numbers, but notice that we can also write, because this is H4, so if we write H4 is this, and H3 would be therefore also UF at T3, temperature doesn't change. So therefore, one can write a relationship between H4 is H3 plus P4 minus P3 times VF at T3. So this is how the liquid enthalpy is calculated. A little bit complicated, but you can go revisit chapter 3, which discusses this in details, and find out how to find enthalpy of a liquid. So to complete the problem, we already know H3, we know P4 and P3. The pump raises the pressure from 100 to 100 to 4,000, and VF at T3, that's the only number we need. So H4 is H3 plus pressure difference we already calculated H3 to be 417.5, and P4 is 4 MPa, which is 4000 kPa, 100, and VF at T3. So we can go back to the table PC model. Remember, at state 3, we had saturated state at 100 kPa, so the temperature was 99.63 and VF is 0.001043. And when you calculate that, the contribution from this is really small, as you can see, not much, and H4 turns out to be 421.5. So now we practically have calculated all the states. So now we can go calculate the heat out, Q dot out, as m dot H3 minus H4, and W dot pump as m dot H4 minus H3, the bigger minus small, and we have all these numbers now. And what is Q dot in? M dot H1 minus H4, the bigger one minus the smaller one. So let's calculate all these numbers and write them down. We get a Q dot out of 2037 kilowatt. We got a pumping power of 4.1 kilowatt, and Q dot in of 2792. Notice how little the pumping power compared to the turbine work we already calculated. Where was that? 758 was the turbine work, and look at the pumping work, 4.1. To find the thermal efficiency, everything is kind of done for us already. So thermal efficiency of the Rankine cycle is W dot net, which is turbine minus pump. So you can do it various different ways. We can do like this way, or we could do it q dot out by q dot in, whichever you find easier. So both will produce obviously the same. If we substitute the number, w dot t minus w dot p, w dot net is about 754, and our q dot in is 2792, approximately 2792, and that gives an efficiency of 27%. If we go this way, we could also find same way, q dot out is 2034 and 2792, and this will also produce 27%. And the back work ratio is going to be w dot p over w dot t. Notice that in this formula m dot doesn't matter because m dot get cancelled. So therefore, whatever m dot we assume in our calculation, in our computation, it cancels out. So it doesn't matter.